I guess we can start. The goal of today is, of course, to continue our discussion on regression, and we should be able to finish this set of slides or a little bit more, and then probably if we finish everything, then probably next class we can have a quiz as well. Yeah. Or if you don't want, we can delay 1 more week. That should be fine. That should be fine. So let's get started. So we yes, last time we actually get into business of regression, which you also learned it from the other class, machine learning. So I would be focusing on more statistics rather than the mechanics, because I think you know how to do the regression, the details, but rather I would focus on more fundamental. The algorithm, I guess I'll delegate to the other class. If you haven't learned it, let me know. I would just try to cover those. But otherwise, I guess I just try to minimize our overlapping. If you think, you tell me during the break, you tell me whether it's too fast or too slow, because even though you cover the other section, it doesn't imply you know it, right? So, but if you think I'm too slow, I just speed up a little bit. So because we have more material than we can cover. So just to recall why we need regression. Regression is the most common step that you extend your knowledge from the data to the population, right? You learned last class, we talked about estimation and also hypothesis testing, right? Estimation is extending knowledge from sample to our population, right? What we know there from the sample extend to population. And hypothesis testing is reverse. We have some idea what's going on in the population in the big picture. We use the small thing to verify they're right or wrong. Okay, so that's you bring the big picture down to the sample, or you bring the sample back, get to the big picture. Okay, and for the regression is you will see basically is that we build up a model to explain what's going on in the data world and how variables are connected. So that is basically we're building docs, right? And the main thing is to explain the y based on x, and we all focus on only x and y. Actually, can of course you learn machine learning, also the regression, you know, there more than 1x, right? But we focus on 1x first, and the extension is trivial, okay? And in this class or next, we'll focus on the predictive analysis. So we just have x to predict y, okay? It doesn't say if you change x, this is what your y you have, okay? You have no causal implication, because we didn't say about y cos x and x cos y, okay? And the last few lectures, we talk about how we interpret x change to y. We will do some A/B testing and also do some other technique to tell you when the regression will have causal interpretation. And the reason you need causal interpretation, because you need to know what's going on, right? I mean, many of you would be doing AI or LLM every day, and you know AI, LLM, AI just do not think, right? They just pattern matching, right? So, but they did not actually, although they said they can think, but they are still not really thinking as we do, right? They all make mistake, right? Because the way they reward the system, they will hallucinate, right? It's unlike human, we do not really hallucinate that much except at night, right? So otherwise, that's a little bit different. So we will, last time we actually work on the bin scatter plot a little bit, right? We'll go over that a little bit, and then we'll do about the locally weighted scatter smoothing. This will be the simplest regression. If you don't try to impose any functional form, so we just have minimal assumption, and the one you learn in the undergrad usually is like this form, right? That you have an intercept and slope, or you map this form, and you would ask Why we have to learn all this time? Why don't we just go for the simplest one, right? A plus bx, right? The reason is being that if you assume linear, there's a problem of this doesn't fit very well. It's not the underlying thing, you fit the wrong thing, right? So this we make very little assumption and expect good for when you're large sample size, a lot of data, and fitting this will be better than fitting all this. And indeed, you can imagine, actually, you also know that in when you're machine learning class, right? You have a very complicated neural network, right? Or many layers of regression. And indeed, it's very similar to this kind of model. Okay. Of course, it's a many layer of regression, right? Or even simpler, but actually you try to do a non-linear style. Okay. But anyway, so let's get started. So we do the easiest model. I mean, it has been quite a while. Then let me draw a picture because I guess many of you were not able to remember what's going on there, right? So for regression, for the bin scatter plotting, you have two variables x and y, right? So you have you can represent the data in a data point here, right? The one data point here, one data point here, one data point here, right? One data point here, something like this, right? And suppose you draw a line, then you will be something like this, right? This is the regression you learn in the undergrad or in other class as well. Is you try to fit this line, right? And the criteria to fit this line is to minimize the sum of square vertical distance, right? Look at the vertical distance. Some of them minimize is the least square method, right? I hope you know it, because if you don't know, then I worry about the grade of your other class. But this is the way to measure it, right? Because this is your intercept and the slope, just two numbers to describe the whole thing. Okay. And this is the parametric method. We'll talk about this later today. But this is what you learn undergrad. But more fundamental or even more simple way is not to estimate a model like this. Okay. Instead, the easiest model, okay, the easiest model, if you want to predict y, what would the model is? Do it without x, right? The most naive model you can imagine to predict y is just use average of y, right? If you ask to predict y, if x is you don't have x access, right? Then the best guess is to use average of y, right? The best guess you would is to use this y, right? Y is the y bar, right? We'll call, right? This y is average. This is your best guess, right? This is the one that you compare, right? That's if you know machine learning, this is the baseline, right? This is the base sum of square error you want to minimize for different thing, right? Minimize the vertical distance, okay? And this is the baseline model. If you want to predict y bar is the thing that if you don't use any x, okay? If you use x, you can use a later line, okay? But if you don't want to impose a line condition, you can use grouping. Easiest is to divide them into group. Say instead of using the raw y, what you're going to do is to divide the data, say, into several parts. Suppose I'm being lazy, I just do one part, right? So suppose I'm super lazy, I just divide it into high x or low x, okay? This low x, this high x, okay? Again, I use the most naive estimate, which is the y bar, right? But y bar, average of y within each group, okay? Use the thing within x that gives me the model like this, okay? I would have a line like this, okay, which is average of y in this large x, and another one is average of y in this group of x, okay? So this is the bin scatter plot, right? You divide them into two parts, okay? And calculate average of those, okay? This is the easiest model you can imagine, right? Because that is done without any assumption, except you think the grouping would be a meaningful, right? If the grouping is meaningful, this is the best you can guess, and then this is minimum assumption. You don't assume they are linear related, right? There's no assumption on how they're related, is it linear or not, right? Just simplest model you can imagine. Okay, this should go before the regression, right? But so that's why we talk about this, right? Is that okay for this one? So basically, the group mean, right, is mean of y, but based on the value of x. Okay, of course you need not do two group. You can do high, medium, low, or any other shape. Okay, and here, and I don't have time to talk about this class, but you can imagine here, what I do is I have to group in a continuous manner, right? Low is low, high is high, right? So, but if you probably also learned that in the regression tree, you allow, oh yeah, but if you do regression tree, you allow grouping into this connected section. Maybe this group and this group is group one, and this can be group two, can be anything. Okay, that's a regression tree. If you or I don't cover in my class because I used to cover in my class, but now you learn the machine learning together, so I just happily I can skip that. So very happily I don't need to talk about that. But that will be the, you can look at the book or you can chat the AI or that would be simple. Okay, but that is the baseline of what we are doing. Okay, so I think we covered this at the very last minute. Is last time we look at again hotel in Vienna, right? And look at the 3 and 4-star hotel and the price below 600, and then I divide in two parts. One is close to the city center, 2 miles. One is far away. Okay, if you believe that the distance is sufficient to explain the price, okay, of course there are many other things, but just focus on one, and then this would be doable. Or you can divide it into 4 parts, right? 1 mile, 1 and 2 mile, 2 and 3 above, right? That will be done. Okay, and of course you would ask, is it the best way to cut the bean? Doesn't really matter. We have to make decision where to cut. And if you learn machine learning, then you know where to put, right? Because you learn machine learning, right? So you can decide, suppose at one cut, you can decide the cut that minimize the sum of square error, right? I think you learned that, right? At least, right? So you can also use machine learning, use cross validation to do it. Okay, I'm not going to talk about those, right? Not my job. Okay. So you ask other teacher if you want to know those more. But I assume I tell you this is the thing, you just do it. Okay. How to calibrate is not my job. Okay. So let's go to this slide again. I hope you now, of course, know NumPy and Panda, right? You know the data. We have seen that many times already. Okay. I'm not going to run this code because I ran it last time already. Okay. And this is the filtering the data. By now, you should know the LOC selecting observation. And you take the hotel, take the Vienna, take the stars, and 600 below. Right? We ran this already last time, so I'm not going to do it. And I do the distance within 2 miles. I call it close. Otherwise, I call it far. And I change to category data. The reason I do that is because of you do it, then you can plot the graph much nicer. Otherwise, yeah, some issue there. Okay. And what I'm going to do is, because I group them, right? Because I group into different group, each group I calculate the y bar. That's what I'm doing. I group them by distance, far and close. And I calculate the average price. Use this AGG price, losing the mean. Okay. And then I reset the index because I just have 2 things, right? Because I aggregate. Okay. And once you see, there's only 2 numbers, right? Close and far, right? And I have 2 numbers there, right? And actually that's done, right? The model I have already. So if you tell me your distance from the city center is within 2 miles, what's my guess of y? Just close, right? If you ask me what is the guess if I more than 2 miles, my guess is 91 euro, right? That's my model already. Okay. Do note that this is a model. Why is a model? Because our data doesn't cover everything, every miles. Our model actually extend to infinite many possible cases. It is not covered by data. So by model, which means that we simplify our world, right, from data, right? Because data can be very complicated. But now we simplify the model to just 2 numbers, right? So that's the beauty of model, because you no longer have to, you can throw away the model, throw away the data. This is the model you have, and that's done. Okay, if someone asks you, what is your expected price of the hotel if this is 1 mile within the city center, then you know the answer, 1.5. If they tell you 4 miles, $91. Okay, so on and so forth, right? So you know the answer. Okay, so this is the model. Of course, you can, this is too simple. Maybe you want to show it to your boss or your client to a better way, then probably you want to draw a scatter plot, right? That would be the one we have done. I guess if you do your assignment, then you should be able to do it, right? Unless you are, I think, not deadline yet, right? Still have. Okay, if you do assignment, then you should be able to see this. You have a map, then it's okay to cover it again. So import matplotlib py plot is the scatter plot. Okay, you can plot anything 2D plot using this. Okay, and you tell him what is the list of x coordinate, what is the list of y coordinate. Okay, you plot using scatter plot, put the x coordinate, y coordinate. This is just declaration where you put the x label and y label and then so, right? You can forget about this. You just plot them, right? And this is what you get, right? Close and far. Okay. So that would be the idea. So that's the reason why I need the categorical data, because otherwise they can put far and close, they can swap. Doesn't look as good as you want. Okay. So this is the reason I do that. So you can also use the subplot idea. This would looks better because it allows me to plot with so you see is with numbers on. Okay, so that is you have to use a more syntax, and indeed this is the syntax that usually you do matplotlib. The one I gave you is a very basic one. Okay, this is if you try to look at all the menu or you even ask AI to generate, this is what you will see. Okay, and what they do is you have to again same as y, but indeed you tell them plotting multiple subplot. Okay, and then you will return figure and axis. The two things you can control. Okay, because I want to add more things, so you have to have two things you have to handle. So this comma, this means this subplot we separate two things. One is a figure, one is axis. And axis I will plot the scatter plot. Okay. And then for the axis scatter plot, I would just try to put the names on. Zip is trying to probably learn in other class as well. We just try to pair them up. So if your one pair is 1, 2, the other pair is 3, 4, you zip, it means first of the x and first of y combined to 1. Okay. Okay. Will become the loop over there. Right. So let me say it. Okay. So suppose x is 1, 2, okay, and y is say 3, 4. Okay. The for loop we'll be doing is I get the first element in the x and first element y that we store as our first xi, the first element there. Then I will just intonate, means I write down the thing, I round them to the integer, and then make it string, okay, and put it in that location. Okay. And then the coordinate is given by data, and this size of test, and test coordinates is some offsetting the point there. It's because I get from 0. So that is the way that you would get the number on. Right? And of course, you really don't need, for this one, you don't need to, you just copy because you just apply every time, right? The only thing you might change in your application, it just changes this 4, the size of the test to any other number that fit your thing. Otherwise, this code you just copy and paste, right? There's nothing, to learn. Maybe you can learn, but there's nothing to really to worry about because you never change this setup anyway. Just like the app, right? You press this button, this comes out, right? You don't really too much worry about that. But if you worry, then you can ask AI. AI is very good at explaining this. Or if you don't satisfy with my explanation, and then label, there's nothing new there, right? So let's give you this guy. Okay. So once you have that, then we can do 4 beans. They're the same. Okay. This is so similar, though. I'm not going to go run the code. Okay. But you should be able to see what I'm doing is using 4 different if statements to allocate it. If it is less than 1, okay, I put 0.5. Why I do that? Because when I plot the x coordinate, I want to use the midpoint, right? Between 0 to 1, the midpoint is 0.5. And if between 2 and 1, I put 0.5. Otherwise, I put what I have before. If it is 3 to 2, I put 2.5. Okay. And it is beyond 3, I put 5 because the data is from 3 to 7, the midpoint is 5, right? Because I plot a scatter plot. That's only true. That's only needed because I plot a scatter plot. Okay. Otherwise, if you plot histogram, okay, then you don't have to worry about that part. Or you put a line chart, then you don't have to worry about that. But because the textbook used the scatter plot, so I just follow. Actually, I don't think the scatter plot is the good thing, good thing, but anyway, I just follow textbook. I need to illustrate because I think it's better to use the one I already is a line plot is better. But anyway, whatever. I just follow the book. And set a category, okay? And again, the same thing, you just set the price, right? Now it's 4 and 4, the same thing. Okay, nothing new there. And once you plot, this is your model, right? So for not both 4 number, right? If your data is between 0 to 1, this is your number. 1 to 2, this is your number. 2 to 3, this number. More than 3, this is the number, right? So that's the model. Your model is given by 4 number. And this 4 number is given by the mean within that range. Okay. So that's why this is the simplest regression model you can do. Okay. So don't underestimate the power of this. Okay. And indeed, if you have a lot of data, this is the simplest one you can do, right? Because linear model, you assume that straight line, right? And this, if you have a lot of category, actually this is fit very well, very nice. The only drawback is you don't have enough data. If you don't have data, this is always very good. Okay. And this is already done. I'm not going to repeat, just getting the same thing, getting the labels. I don't want to bother you with that, but this is what the model you give is like this, right? Okay. And here is the model that I would like better is I would draw a scatter plot and put a line there. So this is one of my favorite, but the book doesn't give you this thing, but I like this one. Okay, but it's up to you. It's not what you like is it's very personal, right? So here is I do the same. I do the original data. I have the subplot and I do a scatter plot. So this is standard scatter plot, right? And then I do a label X and Y, and I put here, I put the Y limit is 400 because I don't want to show anything beyond 400. The graph is not nicer. Okay? This is just saying that I don't show anything the price more than 400. But just if you don't have that, the graph is less more spread out. Okay. And here is I try to plot the line. Okay. What I'm going to do is these are the endpoint, right? 0 to 1, 1 to 2, 3, 2 to 3, 3 to 7 is a line, endpoint of the interval, right? And what I'm going to do is this is the number that coming from the average in each group, right? In the 4 group. What I'm going to do is I look at a line. I try to start to draw from the X start and end, right? Here to here. And I draw according to height, right? From 0 to 1, I draw the average of the price between 0 to 1. That's the Y value. I sit in the free one, right? So basically I get this, and the number H is this guy. If you don't see it, H is this guy. So what I'm going to do is I get 0 and 1 and get this guy, right? So that is how I draw the scatter plot. I access a plot. I draw a line there, okay? I draw a red line there, X and Y, okay? And X is starting point, ending point. The Y doesn't change. So this is the coordinate. And once I have that, this is the line I have. Okay. So this are my model together with the data, right? So if you tell me your distance from city center is 0.8, this is my model. If 1.5, this is my model. If 2.1 is my model. If 5 from 2 is my model. Okay. So I collapse this whole big data into 4 lines. Okay. So this is the easiest thing you can imagine, right? Although seems to be very stupid. Okay. again, you may ask, if it's so good, then what's the problem there, right? Why we don't always use this? The main problem is in one dimension, that's no problem. Easy. If you have more than one dimension, that's an issue. Why? Because imagine you have a X and Y. You cut it into many different bins. If you two dimension, you have many. So put it this way. Let me draw it. The problem is when you say suppose data is like, if you cut, right? You cut this based on X, right? You have many possible cut you can do, right? X1, right? When you have another data set X2, you have to cut it into many different area, right? But it means that all this kind of plot square have to have data. If your data, then your model say nothing, right? So you have to have a lot of data. If the data is a lot, then your model will be very good fit, right? And that's the reason why you learn other machine learning thing, right? Instead of going into all the bins, regression tree or other random forest, right? Other method will tell you how you can do it in a less number of rectangle. Okay, you can imagine if you have X1, X2, X3, X4, many dimensions, then you have to make sure every bin you have the data. But that's not that easy, right? Of course, if you have data, then there's no problem. But if you don't, then you have to figure out how to do it. Okay. And the other one, I think appear in the textbook. Okay, is I cut into multiple bins, right? But the thing is, the problem is it's not continuous, right? You can see the graph here. Okay, from here, the data, the one drawback is what happened. Your distance from the city center was one hotel is 0.9999 miles. The other one is 1.001. Okay, the price you see will jump, right? You across a little bit, right? The boundary will change a lot, right? There's no continuity there, right? So that's why this may not be very good, because I don't really like you just say just across the road, the price change a lot, right? But of course, in Hong Kong, many house or hotel like this, but right, doesn't make sense in other places in the world, right? So so that's why this doesn't make too much sense in many application. So that's why we have another thing is called Lewis, okay, which is try to fit a line that's continuous. Okay, let me show you the graph. The formula as a black box is invented by 1970s, but the textbook even don't talk about how to guess it. We give the Python code to get it, but we will not tell you how to get it because the formula is too complicated to be covered in our lecture. Okay, but I give you the graph. It will look like this guy. Okay, the goal is to find a line that would best fit this thing, and how do you best fit? Forget about it because we're not going to talk about that. But that's the way to do it, and I tell you how the Python code to map to it. Okay. So you can see this is a little bit funny in some sense, because once you fit this, you see the price actually drop here, and suddenly it goes a little bit up, right? So is there some problem with this data, right, or something? But that is something they have to keep in mind. I mean, this best fit doesn't imply the best. Okay. So that is very simple. Actually, it's just one or two lines of code. So don't worry, it's very simple. The thing to do is I will use a statistic model .api called SM. Okay, you can call whatever name you call. Okay, stat model. So that's why SM. Okay, and then I have X and Y. So what you do is very simple. I just use SM dot non-parametric dot Lewis, give me Y and X. This fraction means how smooth you want it. Okay. And you can change this number is up to you. You have to have fun. You can play around with this number. It tells you how fit the data is. And once you fit, already done. It's over. Then you just give me what is x plus y. I can just plot it and I'm done. Okay. And this is how I plot the data. Set the plot. I plot the data, and this is the same. This is where you get the answer. Okay. So that is something too easy, right? This is the model. You're done. We're done the model. Maybe I run this line to make sure that you see what's going on there, because otherwise someone would complain I'm going too fast, right? So let me run this code directly quickly. And then we can have a happy break. Why not exist? Someone kill my thing. Let me check. This is 4. Yeah, this is the code. I don't know why it doesn't work at the beginning. So let me download the data. Just wait a second. It's loading. Okay, it's done. So let me continue to do this part. I clean the data, and what I'm going to do is immediately jump to this one. Okay, I run this one. Okay, so this will give me this one. Okay, this one is so now instead of 0.5, I do 0.9. So let's see what you get. Suppose I have 0.9, it will be less smooth, right? If I increase this, then it will be not moving that much. Okay. If I change to 0.1, okay, then you will see it's more wiggling. Okay. So that's why you allow any freedom to the data, right? If you trust your data, then actually you can make it as low as possible. When your data contain noises, then you should make this number higher. Okay. And something recommend, I think the textbook tell you is like 0.4 to 0.6 is a good number, but it's up to you. It's what choice, right? Like all the machine learning model, there's a hyperparameter you can feed, and it's your decision. Okay, of course you can do validation method to figure out what's the best. Okay, but here we don't do validation, so just do whatever you like. Of course, if I give you assignment, I'll give you the number, right? You just feed what I told you. Otherwise, you don't have to worry. If I don't tell you, you can just feed whatever you like, right? So that's a model. Okay, so you can see what is inside in this thing, right? Just try to show you what do you see. Why? Show you the just want to show you what is there, what is inside this guy. You can see this guy will actually provide you a table from X, all the values, and you can look at Y, you can provide all the value as well. Okay, so this is your model, right? This will give you all the points there, but of course you already plot it in this way, right? But this is the model they give you, right? This the smooth y bunch of y and x bunch of x there, right? It tells you how you can smooth those. Okay. But their model, right? So I think we already covered two regression model. Okay. And both of them are things that you haven't learned, I hope, in your, at least not covered in your undergrad, right? So this is a master level 2 regression. And I think it's not covered in the machine learning class, so it's not too much duplication, at least, right? But after the break, we have some duplication, but you can tell me whether I have too much duplication or not, okay? After the break, which is 15 minutes afterward, we will be working on the basic thing you learned in regression. I will try to be fast a little bit, but if you tell me if this is too easy or too hard, I can adjust, okay? So I'll see you in 15 minutes later. So in the meantime, please feel free to fill in the U reply so that I know what's going on. Okay, see you in 15 minutes. Yes. 第一個係冇版式，第一嗰個咧，只係話你一堆好似分佈咁樣，你只係對 x 分開咗啲字，咁你 average 除咗 y，咁就係你個 model。咁就係你個 model，呢個就係你個 model case 嚟。咁呢個咧就唔係咁嘅，呢個係一個連續嘅，你 fit 一條 curve 嘅，所以佢係連續㗎嘛，嗰個 curve 係，佢係一連，佢唔會斷開㗎嘛，佢條線係連住去。至於點樣佢點樣嚟咧就唔好理啦，因為你 over 咗我哋嘅 level。呢個係分呢度咁樣一個咁樣可能就諗冇。你可以睇下個 slide 呢個位。幾時用？咪咁咯。第一個就最簡單，因為有咁樣簡單，即係話睇下你有，如果你 fit 呢個咁係個最少啊，呢個咁樣 fit 呢個最少啊心水。如果啲 data 好嗰陣時咧 fit 到簡單，即係你個。即係話佢追女仔嘅話，如果你有錢又靚仔，乜都唔使啦，行埋去搞掂啦，係咪先？如果你又冇錢又唔靚仔，咁你諗下辦法啦，最簡單，最簡單嘅答案。我其實咁係最簡單答案咯，答到你。即係通常我哋所有 regression 都係咁，所有 data 都係咁。data 夠靚嘅，後期一計嘅 average 就搞掂晒咧。就係你啲 data 唔夠靚仔，你先需要各種各樣嘅 technique 去做嘢。
謝謝。我想問單文嗰度咧，我交咗一次啦，但係我發現我有啲錯想再交定，唔知點樣執。
可以再入，我唔可以。
我講唔到。
我教下，教下可以10年。你等一等啊。所以我喺呢度需要使錢。佢係一年先都唔係 error，你可唔使理佢嘅，因為佢有時 Python 佢轉咗啲新嘢咧，做啲舊嘢就係得要靚仔起咗。 係啦，咁所以點解我哋 B.B.、G.D. category 就 categorical 就係咁解，佢哋都係排序。係應該排序應該會得㗎，如果冇，所以正常係排咗出嚟㗎，按住嗰個排序嚟做。係啦，如果唔係就冇事，應該係正常。呢個點解要 categorical 就咁解先會排？如果唔係佢亂出嗰咪因為我諗我哋都學你班嘢，我哋想整靚仔你就試下啦。你個 friend 咧？你老友㗎嘛？佢哋唔係你嘅做嘅，我就問你，因為你哋嚟㗎嘛。佢本身唔係我哋做嘅，而家做呢個係成日街我熟過成係啦。我同佢冇牙齒啊，我同佢冇仇，所以唔得㗎。我唔問人，但係佢唔得閒嘅上嚟，我都唔。我唔會記住邊個，我唔會記住邊個上邊個唔係傻嘅。因為佢老師坐喺個位㗎嘛。大部都有個位置嘅。還咗個位。佢哋都係坐嗰個位㗎嘛，即係打翻大家都係，大家都係坐咗好翻嘅高位。陣間我哋都睇啦，我哋小心。擺喺全部啲位啦，係啊。容易選先生。應該冇嘅。太高啦！ So I hope you have a good break. So let's resume to see how well we're doing. The first comment is slower the better. Okay. So I would try to slow. The last comment, slow the better. Slower, please. Okay. I try to slow to make sure maximize your learning experience. So so there's a, as an economist, you know there's a trade-off, right? I do slower, then I can only cover less material. Okay. It's your choice, okay? Easy quiz. I think the quiz is okay. Everyone get, I think most of you get more than half, right? So almost everyone got full marks, right? It's not a problem. And the quiz, yeah, I mean the quiz is not very difficult. Only 15 questions, right? So should be okay. Quiz next week. It's okay. We can do quiz next week. If you want. But the quiz is about the topic 2 and topic 3. Topic 3 and topic 4. Because every two set of slides, we can do a quiz. Okay. Questioning your IQ. I think our material is not too difficult, I hope. Little bit tired. Yes. May release next assignment earlier. Okay, I can do that. It will be doing regression, so I can allow it earlier. I'm adjusting because I don't know how much the assignment's already there, but I just try to see if I need to adjust, make it easier or difficult, depending on how much I cover. So let's see after this class or next class, I will do that. And as you know, we only have, I think we only 3 assignments, right? The last assignment is optional, so only 2 assignments, right? I think, yeah, the last assignment is optional, there's only 2 assignments. So I think it's okay. So it just allow Lewis actually allow us to fit any nonlinear thing and in continuous way, right? But you use bin scatter, you also have that, but you just don't need, it's not smooth as this bin scatter. So the only thing. And you probably, some of you ask when to use what, okay? It's analog, okay? Suppose I want to meet a girl, okay? I want to get her telephone or contact, right? If I have a lot of money, I'm very handsome, then I just go and ask, I'm done. Maybe that is easy, right? But if I'm not handsome, I don't have money, then what are you going to do, right? You have to use different tactic, right? Send her a flower, try to use different way to make her interest in you, right? So that would be, you need those things, just like data. If a data is very nice, very good, then you simple bin scatter, you're done. No need to do regression, no need to do anything, you're done. That's over. Game over. Done, right? You have a lot of nice data. But your data is not nice enough, then you need a lot of technique like regression, machine learning, all those kind of things to make sure that you get the best thing out of the data, right? So that is why you learn so many techniques. It's because the data is not nice enough. If you have very nice data, then it's over, right? Because suppose you have the data of the world, you have the population, the best case, you are done. You don't need to do analysis because you have everything, right? No need to do machine learning. No need to do any prediction. You get everything there, right? So that I think I hope I answer a question. Hard to understand. So I try to make it easier, but if you don't know, try to write down exactly don't know. Otherwise, I would try to help. So does it produce a constant? It's nonlinear. It's high dimension. Why high dimension? You can see the graph. It's not linear. This graph is high dimension. Oh, you asking whether you allow this to have more than 1x? No, that will be reserved for other purpose. This only fitting is just for one dimension, this method. If more than one dimension, probably you would better use regression tree or random forest, other kind of method. Okay. This is useful for fitting this. And this kind of technique actually a lot of time used for insurance company to fit the life table, right? How long people live and the age mortality table, that is people use it. So it's one dimension. This lesson is too difficult. Okay. Hope that it's getting easier because the material being scattered and the lowest is graduate level. Regression is undergrad. So we go back to undergrad now. So don't worry. It's getting easier. Well, we are not Christmas yet, but hopefully I can grade you A. Something I can't really promise, but I try. Well, I try to give you as much SA as I can, but right, because we don't have limitation on the grading, right? We're not curving. It depends on how well you're doing in your exam, your projects, and your assignment, right? I probably in CHK we do criterion-based grading. So as long as you achieve certain excellence, then you get the grade you deserve, and there's no limitation on how many A I give. Okay, same as Harvard, right? Harvard can give 90%, 80% A. In US, when I talk in US as well, I mean other school, then also the same. Okay. Hong Kong, I think CHK we do that. I mean, I don't know other school. I think yet they have some limitation. But for our class, definitely, if you do well, we can allow you to have a lot of good grade. It's no problem. Yeah. Okay, that's good. So I think it's getting a little bit difficult. It's non-promising. You often. Yes, is it used a lot? If you have a lot of data, say insurance company, when they calculate the thing, they actually use non-parametric method. And the thing is, if you have a lot of data, non-parametric is better because you don't have to assume any special assumption there. It's easier. Okay. And also you don't need to think what kind of the shape you want to get, right? That's why machine learning is also a non-parametric way. Okay. The machine learning is very powerful. Tips and example, I think, and exam tips, well, basically just it's basically we ask is the two part, right? First part will be just multiple choice that based on similar to what we easier than the quiz, I would say. And the non-question will be something I showed you already because I will be just basically just like I give the code, you just analyze based on the code, right? So you don't have to write the code, right? I write the code, I give you the result, you just tell me what you learned from this code, right? I ask question. Probably I'll give you the past paper, but you already seen it already. But because of that, we could talk about that. Okay. Delay the quiz to next week. Yeah. Okay. OpenAI collapse. Little tie is healthy. Yeah. Yes, I think it's fine. Oh, already over mid autumn. I don't know how much mooncake you eat then, but if you eat a lot, then probably you are very tired. I guess that would happen. I go to work by bus. Seriously? I mean, I haven't taken bus for a very long time these days, but I just take the subway because from door to door. So when I take the bus now, I feel very dizzy, so I can't really take bus. Unfortunately, I take the subway more often. Okay. I want a grade A. Hopefully you will get one. I guess it's not, our class is not very strict. Okay. As long as you do revision, I think it shouldn't be too difficult to get an A compared to other class. But right, I think our material is not that difficult. But let's see what we're going to do. Okay, this is something you learn undergrad. If you forget, it's okay. I mean, but if you learn this is the first year undergrad, you have a linear regression. You fit a line to the data point, right? And then let's go back to this is a formula, but let's go back to the screen I have here. What's regression? It's the purple color line. Okay, you forget about the black and the blue, and the purple color line, and this is your alpha, and the slope is beta, right? So what you're going to do is y equal to alpha plus beta x, right? How you fit? You have a line there, you go up and down, it's changing alpha. You rotate, it's changing beta, right? You keep up and down and rotate, okay? And what's the best fit? Of course, fit have to define, right? As I said already, how do you do the definition is called the least square method that would actually use in basically all the machine learning as well, right? You fit, this is a data point, and this is your model, right? This part is, that doesn't fit, that's called error, right? And you took this distance, square it, okay? And you do this for all the data point, sum of it, that's called sum of squared error, okay? Error, square, sum of all, there's a one quantity there. You try to look at the slope and the intercept, change alpha and beta to minimize this guy, okay? And some of you ask me, in the bin scatter, you have a line there, you can fit this blue, right? How can you choose where is the red line, right? If you use machine learning method, okay, you will be moving this red line around. If you move this red line, the blue line will change, right? But each one you have a error here, right? Here, right? And you keep moving until this sum of square error minimized. Same thing, everything can be done in that way. Is that clear? Of course, you don't have to outdo it because it's not my job, right? So, but I will tell you how to do the regression is to minimize the vertical distance, sum of the vertical distance square, okay? Sum of the square, that's called the least square method, okay? Okay, so this is the model, as I said. You choose the intercept, choose the slope to minimize the vertical distance. This is your line. This is your data point, yi. This is your line, right? This is the purple line. This is your data. Squared, sum of. Okay, that's what it means. Minimize the vertical distance. Squared, sum of them. Okay, let me repeat. This is the vertical distance. Square, sum of them. Minimize. Okay, of course, different machine learning will have different parameter, different thing to the model, but it's always what the data and what you predict. Okay, and not going to discuss why you do square, because square just like the variance, right? Have a nice mathematical form, and then you don't want to do absolute value because it's king thing. So that's a math reason. But just this is the model. Okay, this is the slide actually I used to teach undergrad. Okay, so this is the vertical distance. Okay, sum of the square. Okay, up and down. Because you don't want to distinguish up and down, so you do the square, right? Because blue is above the line, red is below, but you don't really want to distinguish up and down, right? And using the math, okay, you can prove actually by calculus or some other math, the slope, the best slope, okay, will be given by the covariance xy over x, the variance of x, okay? And once you fix the slope, then you can just put in the equation, find the alpha, okay? Because the line will pass through the center of data, which is the X bar, Y bar, okay? So that's how you find the regression. Of course, you don't have to worry about this equation, right? Because you always use the machine and click and then comes out, right? But I tell you, it can be done in some way, okay? But you don't have to worry about this guy, right? Because what you need to know is to read the data later, okay? And the idea of the regression, just to make sure you understand, is remember the best model, sorry, the most stable model you can do is Y bar, right? Even though without X bar, right? So that means that you're explaining the variation is in without looking at Y bar, okay? Because this is the thing you're looking at, right? So how you explain the Y is you different from X bar, right? Because X bar and Y bar is within this model, right? The line must be passing through this point, okay? And what you're doing is to say why you predict different Y instead of this guy, because they have different X. X is higher, in this case, X is higher than X bar, and then you predict Y will be higher than Y bar, right? So that's why I said you are using this difference, explain this difference. Okay, this is the model, right? Because as I repeat, you always can use Y bar for sure, right? That's the basic model you are doing to do without thinking about anything. Y bar is your baseline prediction. Okay, so now what do we learn from building this kind of model is to say to see X is different from X bar. If this above, the line will tell you is Y will also above the Y bar, right? So basically, this is the idea of the regression, right? Looking at how we deviate from the X bar and that with the Y bar, right? If this goes up, is this way, you go down, the same idea. Okay, I hope I explained this, but of course, you must have learned that in your undergrad, but maybe this like 10 years ago, or maybe not that, maybe 3 years ago, right? So then probably it's okay. So a few years ago, but probably you don't remember, that's okay. So I will run this regression in the Python, right? So that you will get is you run the regression. This is the coefficient, and this is the slope intercept. So you will see how we get it from the Python, okay? But the key here, actually, I'll ask in the exam as well, in assignment as well. What do we learn from checking this, right? So from this result, we will know the price will be equal to 133 minus 14 distance. Okay? What does tell us? First, our intercept is what? Our intercept with the price that it is at the city center, right? Because there's no distance, right? Distance from city center is 0. So that means that the city center, the price you expect will be 133. Okay? And for each mile you're away from the center, you pay $14 less. Right? So this is the model. Okay? Of course, the model is a lie, but this is what we are saying. Okay? So now let's see how we run this regression. Don't worry, it's very simple. Okay? So we will use what we call the SM again, stat model, .api. So we are basically in our class, I think we do SM all the time from this class and the next class. The stat model, I think, is the most convenient one, at least for our purpose. I think the machine learning, I think they use another one. That is more convenient. There's another one. I think they use the science PY, right? The difference between the two is science PY run regression faster than you run our regression. But when you do analysis, this is better. Okay, because they output many nice things that you need to know. Okay. So this model's API is stat model API, and then you would X is the distance, Y is the price. And here, there's a technical point here because I use the stat model API. I have to add a constant. Okay. That is you need to add this step because of this. If I use the formula, okay, there's another one. I can dock formula, then I don't have this one. But in order to do it, you add this because you learn linear algebra, then you know you have a bunch of one is intercept. Okay, if you don't do this, you don't have intercept. So intercept is a bunch of 1. Okay, add this because you run the regression with an intercept. Okay. Okay, the reason if you don't do this, the regression will always pass through 0. So that's why we have to do that. Okay, because when you run, actually, remember you run this model, you're not just use distance, but you also use the 1 is distant, 1 is here. Well, anyway, so if you don't get it, it's okay. Just keep it in your model. So that's okay, right? And then what you do is you use ORS, Y and X. Okay. Do note that this is small letter, this capital. Okay. This small is capital. You run over capital. And this is, you feed the data and you show the result. Okay. I think I have to run this because this is the first regression we are running for this class. Okay. So I should do it. Okay. So you can see I run it already, so with the answer here. Okay. This is the regression result. Okay. You need to know how to read this table. That's what I asked in the last year exam. Okay. And no, you will see the table a lot of times, so don't laugh because this is what I asked. I'm pretty sure I asked this one. Not the same question, same number. Not the same number, but I will definitely ask this one. If I don't ask this, then what I'm teaching, right? So I have to do this one. Okay. I don't know we'll cover everything there, but I think majority of things you will know. Okay. So I have the price, ORS, and R square. I'll talk about this later. F test. So the key is these two coefficient 133 here, and the distance -14. Okay, maybe slightly different from the number there, but so this later, this is standard error, is the standard deviation for this guy. Okay, there's a formula to calculate that, but I'm not going to talk about those. Okay, but that is actually what I said, the standard deviation of this number. Okay, you can imagine, of course, we don't do it. You can imagine also we do bootstrapping, right? You can run a lot of data, you run many regression, then can come up with different alpha and beta, then give you this number. But this number is calculated in order to see they're different from 0 or not. You can calculate t value or p value. Okay. Either you check t is bigger than 2 or less than 2, or this p value is small enough, right? Less than 0.5% or not. So the p value, this one, is 0, right? Means so small. These things are useful. Okay. So basically, when we do regression, we only care about 2 things. Okay. That is mainly what we look at is this number. This is the first round. We look at these 2 things. This 2 column is the key of our result. Okay. We'll talk about this very soon. Okay. But we talk about how to use this one. Okay. This one is closely related to last class. We talk about hypothesis testing. Okay. We want to see if this model is a rubbish or not. Okay. Is look at this value. Okay. If this is less than 5%, then the model is good. Okay. And you can also see this and other with this one. This is also another thing you have to look at. This guy. Okay. Want to check if this is also less than 5%. But we'll talk about this I think after the break or next class. Okay. These are the number that to determine your regression is a rubbish or not. Okay, because it happened to be this a very last standard error is not so good. Okay. Why this is big? Because the data is very fluctuate, right? It's not very, the data doesn't fall very nicely on the line. Then this thing will be big and this thing will not be 0. Okay. So these 3 things this is checking this one is good or not. And this one checking whole thing is good or not. Okay. This is individual checking item. We'll talk about this later. So don't worry. This will check the whole thing, but we'll talk about that later. But at the moment, you only need to know this 2. Okay. But at the end, these are number you check. Okay. Because when we actually run the regression, this is the thing we care. All right. You read any report, you have to look at the p value. Right. This is a slope. Okay. Another thing we will talk about that if you have time, but if you learn machine learning, right, you often do the log likelihood, the AIC, BIC, R square, they're all there. I hope if you will learn it from the other class. But if time, you can cover that, so don't worry about. because they are important for our purpose also. Okay. So this is the table. Okay. Now, once we fit the model, we want to see how the model looks like, right? So that is nothing new, but we just do a scatter plot. Okay. So what we're going to do is the model, I'll use the predict function based on x. What to do, this is doing is x is bunch of is your data. Okay. And this result of predict means that for each data point of x, based on your model, you predict your y. Okay. This is standard in your machine learning. So you always do the predict. Okay. There's nothing really special for ORS. Okay. And here you can see I use the original data to plot the scatter plot. I use the x and the predict data to plot a line with the regression. Okay. So that once you plot, this is your model. Okay. Your bunch of dots and the red one will be the model. Okay. So remember how you fit this line, minimize the vertical distance, sum of for each point. Vertical distance square, you minimize all the points. Okay. And you don't worry about how you minimize because computer give you. What you need to know, there's a function called SM ORS dot fit, right? Right, you can do this. Okay, this is the model. Of course, some of you is good at the math. You can just put dot fit here, just one line, you're done, right? But I just do several line there, right? Because if you're good at Python, right, you don't have to do this. You can put dot fit here, and one line code, you are done, right? So very fast. Okay, once the data there, right, you can fit it. So don't worry too much about the syntax because you will be doing copy and paste exercise when you do the assignment. So you must able to know how to run this regression. I'm not worried too much about it, right? And in the exam, I also give the code, right? I give the last year, the exam is like this, right? I give you the code, give you this, and ask you questions. Okay. So there's something I expect you to know for the same area we teach. Okay. I'm not expecting you to write the code, right? You just need to know how to use it. Okay. Now, once we have that, okay, we talk about something called R square. Okay, is how good the model is fitting. Okay, so this is the model. Maybe I just so this is a predict model as we said the predict, right? You use the x to predict the y, and that is predicting the ORS model. Okay, and I mentioned in this here we have something we call R square. Okay, and if you learn machine learning, R square is also the way you want to fit the model. Okay, and let me show you what's R square. Okay, although you would not remember the formula, but I can show you intuitively what it is. Then I think you stick in your head. Okay, let's forget about this formula for the moment. Okay, let me show you what it is first, and then go back to the formula. Okay, because look at the table is very simple. Look at the graph is very simple. Okay, remember what I said. If you don't have x, what is the prediction? Y bar, right? Y bar is a model that's most naive. Okay, and what your model going to explain is called SST, right? It's the distance, the row distance from your data point to the mean, right? Something to be explained by your x. Okay, you want to be explained. This is your goal to explain SST. Is sum of square total. This is because you will square and add up together, right? Every data point, you calculate this distance and square and add all data point. It's called SST, right? And you will see what your data have explained for SSR, right? This is what you propose, and this is what you explain is sum of square regression. Okay, this distance square. Okay. And what your model fails to capture is called SSE, right? And remember, SSE is actually the regression is trying to do is to minimize this guy, right? Your regression is minimizing SSE, right? So how good is your regression? It's just very simple. Just SSR over SST, and that's it. That's R square. R square is simply a ratio between SSR over SST. And this ratio must be 0 to 1. Why? Turn out that even though it's actually a square, there's math to show you that this plus this is equal to this. Surprising. Okay. I'm not going to do the proof, but actually you can do the proof. I mean, if you learn undergrad, actually if you do stat undergrad, you prove it all the time, but we are not doing anything. This equal to this plus this. Okay. So that is the formula here. SST equal SSR SSE. SST is your data compared to average square. That's what we write. And SSR is your prediction minus the baseline. What do you explain? This line minus the y bar. And SSE is what you try to do, right? Your data minus the predict one, right? So it's this guy. Okay. Already, I think this way I write down all the thing there. You can check this right, but at least you know R squared is being 0 to 1. 1, perfect fit. 0, worst fit. Okay. The higher the R, the better. R squared, the better. Okay. Okay. So that is what we see, right? And it's SSR, SST, and then machine learning can tell you how to adjust this. Okay. And why I talk about machine learning, because even you run regression, you can do machine learning, right? Because when you have a big data, you have a lot of columns, which we don't write now, but a lot of columns. Which column to pick is a choice, right? Then you can minimize your SSE. That's one way to do it. Or you can maximize R square. That's another way to do it. Because there are many ways, right? SSE one way. But R square is one of the good way to do it as well for regression. But you can, R square doesn't make sense in other, say, regression tree or other thing, right? But R square is good fit for the OLS. Okay. So there is an other formula I want to talk about. Is the MSE and RMSE. Okay. And what are they? Okay. First, SSE, remember, is the sum of square, right? The line and the point square. Okay. And of course, if you have more data point, then SSE is larger, right? So usually you don't actually minimize SSE directly. A lot of time you actually minimize MSE, right? But you fix the sample size, there's no difference, right? But if you compare across different data size, then you probably want to be more careful, right? Because you minimize this guy or minimize this guy, the same thing, right? You have to fix the data size, right? So that's why there's no difference between the two. And probably ask why -2, same as the sample version, because of unbiasedness. I'm not going to talk about that, but this gets better, okay? And you ask why I have to do that, okay? This is the variance, okay? This is capturing one thing. It's capturing variation of your data, okay? What measuring this? I skip an important thing is what is capturing, okay? If you learn for those of you who remember undergrad, okay? This is actually our model we are thinking in our head. Okay. If we run a regression, one of the assumptions why this regression will work is we have to assume the underlying data generating process is following this equation. You give me the x, I multiply by beta, and plus alpha. I want to guess this number, but this number that is deep inside somewhere, right? I don't know the number, but someone tell me the number, okay? It's hidden in the hidden parameter, right? And you don't observe this guy directly, but you observe with some noise. And this is a error, which is mean zero, for variance, some variance. Okay. And this variance can be measured by MSE. Okay. And why we care about this is because of, again, MSE, this one is measuring how good is your regression, right? Just imagine what is here. This is the thing that not captured in your model. You don't have data on those. Okay. Let me repeat what I'm saying. Although we are talking about the best fit line, right? We don't talk about anything statistics at all, right? So let's get back to statistics. Okay. If you assume X and Y are generated by this process, there's a line behind, you don't know which line there, okay? And you have epsilon, maybe I draw a picture, okay? Let's get to some statistics. So this statistic is, you would be thinking is like in the world is there's some machine that generate a bunch of Y data, right? You give me X, okay? This is suppose this is alpha, and this is beta, okay? If in the world there's no error, okay? This error means actually other term that is not in the data, okay? If there's X is sufficient to determine Y, okay, there's no other thing that bother us, you can always observe this line, right? This is, we think this the model, the world work in this way, right? It's a linear world, okay? You don't need to make this assumption when you have a non-parametric model, but when one regression, in your head, actually there's a model behind. This is how X and Y generate underlying, okay? We assume there's something, otherwise we run regression is wrong, okay? We're actually assuming X and Y are related linearly, okay? And of course, we don't observe this line, right? There's some other thing affecting. It's a random term, right? Random term means that you would be not observing this, but rather than along this line, maybe error sometimes positive, sometimes negative, sometimes positive, sometimes negative, okay? So that the orange one is what we observe, okay? And this, right, on average has no effect, right? Mean is zero, and the variance is sigma squared, and how the standard deviation or sigma, right, can be estimated using regression by the MSE you just calculate. Okay, so the MSE is capturing things that we don't capture. Okay, if MSE is large, that means that a lot of things we want to capture, we didn't have data, has a large impact. Does it make sense to you? So let me repeat because I think there's a little bit jump from what we have discussed. Okay. So before we saw about if with data, we want to find the best fit line, right? There's no problem, right? Because we can always do this. There's no statistics, right? Right? There's mathematical exercise, right? There's a line and fit, right? Any kindergarten can do, right? Primary school can do, right? So why do we do this in statistics class, not the math class, right? The reason is because we have a model in our heads. We say X and Y related by this equation. And this is given, this number, the number. What's the random there? What is the probability there? The probability lies in this epsilon, things that we can't observe, or there's something there, right? Remember our example, this distance from the city center, this hotel price, right? And beside the distance of the price, there must be something unrelated, right? Maybe the sunlight on the hotel, whether there's a very noisy or there are many other conditions. It's small enough, but they add up together, right? Many small parts, right? On average, there's zero, okay? And we want to look at how big the variance or standard deviation of this guy, things that we didn't capture. That's measured by MSE. Okay, then there's a model there. Okay, you need to, when you actually run any regression, in your head, you're assuming this is how data generate. It's linear. So that's why when we ask, when we run regression, when we run non-parametric, we don't make this assumption. When we run regression, implicitly, I mean, you have learned this in the undergrad, but probably you forget, but you have make this assumption. In the background, they say actually they're related by line. Okay? Is that clear? It's okay, you don't fully get it. We're not asking the fundamentals, okay? But what I want you to know is this MSE is capturing one thing, is the variation of the thing we can't observe, right? So basically just how good is your model, right? Respect to what you can observe, right? If you can't observe a lot of stuff, this MSE will be big. That's what I want to say. Okay? This is the variance. This is standard deviation, right? So you want to look at this number. Why? Because it will appear in your sometimes appear in regression. Okay, it's not here, but this is something you do, and I think you also learn it in your your machine learning class later. Is you also minimize. Sometimes you minimize this guy. Sometimes you minimize this guy. Sometimes minimize this guy, and there's some reason why you choose those. Not my class, so you will learn from those other class, but this actually you will do in machine learning. Okay. Okay, so that's why I mentioned, because all the machine learning you can imagine at the background is there's some data generation process, right? You have to your data only capture some of the details, but something is omitted, right? These are the things is skipped. Okay. Okay. Now, this is the model. From the data, you can read what's SSR, STT, SSE. You can get R square, MSE, right? Because they all come from the table, right? You can have R squares here, okay? And here is the formula how you can calculate SST, SSR, SSE. Just the Y bar, mean, and calculate the difference, and just follow the formula I have already. Okay, so this is square, right? And sum of them, right? The sum of square is actually the formula directly. Okay, is that okay? I think that's okay, right? Just because this is SST Y minus Y bar square. It's just actually this is actually come from this formula, right? If you Y minus Y bar square sum of, right? So that is you basically convert this to my equation, okay? And R square is this over this, but don't worry, this is always you just copy and run, copy and paste in the code you can run. There's the same thing, okay? But the formula I explained to you already, okay? And that's how you calculate R square already from the data, and you can calculate the MSE and RMSE, okay? And this tells you how good is your model, okay? And so I think you learn in this machine learning class is the skip learn. This is more, I think this is more familiar with you, but that will be the same idea. Okay. You will do the prediction, but I will just skip this part. Because I don't, you think you run it in diagram, right? Say, when this is the purple color, where QT title, you can skip because this is, I just put it there for you to reference for the other class. Okay. So I'm done chapter 7. Okay. So you can see I also have this last slide. The break is the SIC kit learn. You can see the regression score equal R square, right? So that means that actually you do machine learning using R square as the method. And also you can do the mean square error, okay, as the way to map the data, right? Actually, you can calculate this using the skip learn method. Okay. So why I talk about this? Because it's you will use it for machine learning, right? So that's why I talk about what are these, right? You want to minimize. Remember, what are these? Mean square error is capturing what you haven't captured in your model. Okay. Let me repeat. They are capturing what you didn't capture in the model. Okay. And R square is how fit is your model, right? So I hope I give you the answer. Okay. And after the break, we talk about chapter A, and that we will go a slightly faster or slow. Let me know. You can tell me, do the review reply, is it too fast or too slow? And because chapter 8 will be just some simple way to transform the data. We are running a regression, but instead later you will see we can do a lot of crazy transformation, like taking log and square things and make run different regression. Okay, so that would be something more like mechanical applying new things, but not something, no new knowledge to learn, but just some features you want to click. Okay. Okay. So let's have a break of 15 minutes and we come back. I open the U reply so that you can complain. Maybe a second break. Is it good? Be easier. Okay. There's only 5 questions. If you want to complain, feel free to do it. Let me know whether too fast or too slow, because I don't really know how fast I should go. 我以前你係重多人，你大家上面呢個可以都講花水擺都係所以你幾萬幾多人？應該就冇晒，一可以有時我哋係抄我哋呢個有識講嘅呢個識講嘅，一啱就呢個咩嘅。都抄咗份嘅。好啦，我哋其實我覺得係大家。OK， 有時我都冇攞出嚟，個時間寫曬，我冇加埋執埋佢。因為每一你嘅課，因為我時間到咧，前幾年佢哋 iPhone 佢係後邊嗰我就係個最 iPhone 做緊時間，所以有時係嘅講聽嘅，佢 work 到嘅，可能你記得即係你個 Python 可能而家新用戶佢都係先。即係等於都係佢正常 AI 過嚟正常，我哋即係咩影相係精簡過嚟，可能精簡。係啊，佢個啲水呢度都係講到你個叫相對嘅。應該冇嘅，我哋可以比較花。即係拉佢。係啊，係咪呢個咁樣講？差唔多頭先實情況。你想直接睇樓盤，喂，拜拜，B.B.A 落去。 Not sure you have lost your complaint. Is it too fast or too slow? We only have 9 data points. Okay. So we learned the concept of R square, MSE, RMSE. What do they mean? Okay. R square, as I repeat, R square is how good is your model, right? Because this is percentage of thing you want to explain. If R square is large, that means that your regression is good, right? That is, I have good confidence of our model, how it fit, right? So remember R square, what does that mean, right? Is R square is simply is the total of what you explain over the percentage you have explained, right? So if R square is high, that means that your regression is good, right? So remember, if R square is 1, that means that your line is perfect. Your data for every point is fall on the line, so the best. So that's why R square is also known as goodness of fit, how good your model is fitting. Okay, and that means that how much confidence I want to put in the model, right? If R square is very low, then probably I don't trust the model that much. I hope I answer a question. The second part of the question is why we care about MSE, RMSE, what do they mean? Okay. Later you will see is we want to use this model, okay, to say pick up what is a cheap hotel or a good bargain hotel, right? Later you will see if this is a model, okay, this is very bad deal, right? Because you expect price is here, but you are overcharged, right? And of course, this model will tell us how good this line, right? And if you're way below, then probably these are the good deal, right? And our MSC and MSC is asking us to say, because we only use this distance, right? And we omit a lot of stuff, right? So either you omit because of your choice or because of many other reasons we cannot measure those. Then we want to see, as I said, our MSC and MSC looking at what is capturing the thing you didn't capture in your model. So if they're big, then you don't have trust this line that much, right? Because you miss those things, right? So if RMSE and MSE is very large, then probably you will not take this too seriously. But if it's small, then you probably this is a good guidance of what the world should be. Does it make clear? And again, this also related to machine learning class, which I got a disclaimer. Okay, is if you do machine learning, right, you can fit based on MSE, right, because you can minimize SSE, right, but you can also minimize MSE, the same thing, right? But sometimes why do it? Because when you minimize MSE, then the quantity much smaller, right? You divide by n, so it doesn't expand like crazy. And our MSE will take a square root, then the quantity much smaller, the maximization is better. Okay, so actually that's the same thing, right? You just one is divided by n/2, one is take a square root, so that's different thing, right? MS is measuring R squares, measuring something very similar, right? Because SSE over SST is R square, right? So they are always similar. Okay, but they're all measuring how good your data or how good your regression is, and test your confidence over this regression. Yeah, because you have the model, then how good the model is, right? You have to tell. Just same as idea. If you're given data, your boss, your client, or someone asks you, what do you learn from data? What is your first response? Give me the mean, right? Give the median or whatever. That's just like central tendency. And the second question, this is your guess. The second question will be, how good is the number you give me? Variance, right? Standard deviation, all this kind of thing. Same. The regression, I tell the line, how good is that? R square, MSE, SSE, RMSE. That is, you tell the people how good is your model, right? You can't just say, it's a model, trust me, brother. No, doesn't work, right? I mean, you have to tell how good is it, right? This is R square, RMC, this is what it is. Same as why you have to learn variance, right? Why don't we just learn mean and say goodbye, right? Over, class over, right? No, we have to tell your user how good is your model. Okay. Can we go before 9:30? I think you can go before 9:30, but if I go before 9:30, then probably someone complain, right? But I mean, feel free if you want to go, just no bad feeling for me, okay? I get the same wage, so just go if you want. If everyone go, I'm very happy. I have to stay anyway, so even if everyone is gone, I have to be here. So it doesn't really matter to me. So the hotel case is SST, SSR, SSE. So the question was SSR, SSE. So SSR and SSE by itself usually don't mean too much, right? Because you really want is R squared because it tells you percentage term. It's easier to explain. Just like correlation coefficient. And you don't use this directly, right? You maybe what you compare SSR or SSE, usually you have two different regression model. You compare two different SSE and SSR, that's how you compare. By itself, the number is not easy to say, right? Suppose you take exam, you get 99 marks. What does that mean, right? When you have to compare to your classmate or compare your previous performance, you can say whether 99 is good, right? If everyone got 100, 99, you're the worst in the class, right? So have to be compared to other benchmark. Same as when we say SSE is this or SSR this, right? See this table, if SSE, this model they give you, right? You may want to run another regression, use different X, right? And later we talk about different kind of format, then you can check whether SSE is good or bad. How many assignment? 2 or 3? As I said, there were 3 assignment, only 2 will be required. The last one up to you whether you want to do it or not. The last one will just bonus point, right? Or if you do 3, we'll take the max of the 2, right? So that would be the thing. But I know you guys are busy, so that's why I make the last one optional. Okay, if you time, you do it. You don't have time, you don't just forget about it. We release the solution before the exam day, right? So you will see it. when could know if value could, again, is R square is from 0 to 1 is easy to compare, right? But MSC, RSC is comparing different model, right? Only if you're model 1, model 2, model 3, you compare them. I think you learned in machine learning, right? You have a linear regression, you have a regression tree, your random forest, and you compare SSE, right? You compare different type. I think you have that already. What is the flow in order to validate our data? Then validate our model at last row the insight. That's what we do. First you do, that's what you do in this class. First, chapter 1, look at data, garbage in, garbage out. Second, look at EDA, look at the study data with the outlier, check out things, clean everything up. And then you want to look at the mean, the variance, look at correlation, right? Once you have that correlation, you see how they're related, you can run regression. And once you run regression, you can look at the R square, look at MSE, RSE, then you run different model structure, right? And then you see this, right? Because it depends on what you look at. I hope I answer your question. And you can check the textbook. I think the textbook, chapter 10 or 12, they have a very clear flow of how you do data analysis. I don't know whether our slide will have that, okay? But if you can't find the chapter, let me know. I can show you. The quiz is next week or next 6 weeks. I want next week, but you guys want next week, so next week. Okay, let me finish this slide. If I finish the week after we finish that set of slide, okay? I don't know how many next I want, but or you want. So either 21st or 30. Which one you prefer? Huh? Okay. Who want A and B? Who want A? Who want B? 25? Okay, 25? Maybe I just vote, right? Let me do a vote very quickly later, okay? Very soon. R square, no further linear regression. Let's do one question. Let's do one question. 2. 23rd. So let's do a vote for 2 minutes. You tell me we follow majority rule, okay? So 23rd or 30, you decide. So remember, you only need to score half of the quiz question to get full score. So 15 multiple choice question, you answer above 8, you get the full credit. Every 2 set of slides with 1 quiz. Hmm? Huh? Hmm? Lesson 5 and 6. No, topic, number slide. So we are only the 4th. This is our 4th slide, right? So the quiz will be slide number 3 and number 4. So just basic regression. Oh, it depends on how many topics we cover. Okay. If we don't, but of course, I think at least three quizzes, right? So people's voice, right? We respect. So we will do the quiz at the very end of the class like last time, okay? We'll do that. So the quiz will be hypothesis testing, estimation, and regression. So up to the probably up to the end of the day, okay? So remember before the break, I said one thing. When you run the regression, we have to assume underlines a line, right? You would think this is a big restriction, right? But we didn't say what x is. You can have x is squared x or log x. You can do transformation on x. Okay. Why that's the case? Because if I have the data is look like this, say, suppose, right? Look like this. Look like this kind of style. It's my data. Maybe I just draw it better. Seems to be not good enough. So data like this. Right? This look like a parabola, right? Doesn't look like linear, right? Then you fit a line, you can still fit a line, but doesn't fit very well, right? So you may consider fitting a polynomial is better, right? So we actually allow the model, something like this is allowed, right? Y equal to alpha beta x squared plus epsilon. That's okay. You can fit that. No problem. You can fit that. Okay. Or even better, you can fit more than this. If you learn multiple regression, you can fit any polynomial of x. Okay. So now we are going to talk is allow us to do some transformation of x. Okay. And there are some transformation better than others, but we'll tell you how to do some transformation. That actually what we're doing is to make our regression more versatile, okay, and fit a better form, okay. And probably you ask which form is to pick. That is the question being asked. R square, MSE, SSE will be a judge, right? If you change the format, while you map x, while you try to regress on x or x square, you take the log or you take square root while you do the transformation. And which one is better? What's the tell? R square, MSE. Okay, this is the thing can tell you which regression would fit. Okay, and there are many things you can do. As I said, there's a constructed cubic, or you take a log, or you can do some what we call piecewise linear. Okay, if you have time to cover. Okay. So very often when we run regression, we take log. Why? Because log is in finance or in math. Log is the growth rate, natural growth rate, right? It's called the percentage change, right? So if you look at the stock price, it's not. If you try to model the stock price, as I said last time, it's not good because it can't go to negative, right? So the easiest thing to do is log of the price, but look at the log of the price, which is the return. So whenever run regression in the finance, you notice they don't The Y they use is not the price, but rather the log of the price. Why? Because it's a return, and return much nicer, right? Because it can go negative, can go positive, right? So that is why we want to do that. Okay. And you take log, also can take log on X as well. So that usually you can see mix and match. Okay. You can do the baseline. You can just log X, you can do log Y, you can log both. And the question again, which one fit better? R square. MSE, right? RMSE. You can tell which one fit better and use the one that fit the best. Okay. Because you can have many models because no one knows what the actual model is. Okay. Because by running this model, you are saying that this is not X determine Y, but rather the percentage change in X determine Y, right? So this means that X changed by 1, Y changed by beta. This means that X changed by 1%, Y changed by beta. So it depends on how X and Y related in your feeling. Okay. And here is change 1 in X, change to Y in percentage change term, beta. Right? So that is, what does that mean, right? Increase X by 1, Y will increase by beta percent. Okay. And this means when X increase by 1%, Y will increase by beta percent, right? So is you decide what it is, because if there's no theory, you have to come up with your story. And if you don't have story, R square is your story. Okay. The best thing, of course, is come from your domain knowledge. But if you don't have knowledge, you have to rely machine learning idea, R square, SSE. Okay. I hope I somehow answer your question. Why we care about those. Okay. So remember this baseline model, price and distance. Okay. And again, hotel data, I'm not going to do this. I do it too many times for this slide. Okay. Again, this slide I've seen too many times, right? I don't want to do it again. So here is another thing that is called the stat formula API, not the stat model. Remember this one compared to one we learned before. So we have the stat doc API. Okay. But the other one that you can use is called, actually, I think it's more convenient. It's called stat formula API. Okay. And this alternate, because there are two ways to cite it, that's why I do it. Okay. And you will see why I don't do this, because this is a little bit slightly more complicated. You call the SMF, stat model formula, the ORS. You tell them the data has price at distance. So you run price against distance. Where is the data? From DF, you fit it. Okay. So one line code of running. Okay. And later, if you run multiple regression, you just add a plus sign and add many columns, you go on. Okay. So this is the most convenient when you do that. Okay. The reason why I show you the both, because actually it exists in that two way to do it. So I think this is less elegant. So when you have simple case, when you have more, then this is, I probably will use this formula API for the rest of the semester. Okay. I think we'll do this line of code, but it's slightly more complicated. Okay. But in this one, you don't add the constant. It's there. And once you run it, you run the summary. This is the same we have seen. No difference. I think the same. Okay. But I show you the formula.api is more convenient. And maybe next year I should only talk about formula API. Okay. Because I guess no point to talk about two different ways to do the same thing. Okay. I don't know why I talk about this, but anyway. And you have X, you have Y, you can predict, right? Oh, I see. The reason of doing this, because when you do prediction, you have to put in the whole data frame. So slightly little bit different syntax. Okay. And you can do the distance plots, right? You can scatter plot, and you plot the line based on what we predict. That's the same as previous thing. Okay. And this is the regression line, the same thing. Okay. Nothing new there. Okay. This is what we have in the before the break. So now what's new is instead of price, we want the log price. Okay. So you run the same thing, but now the y is not the price, but take the log of the price. So that's very simple. And we'll show you the regression result is intercept is 4.84 and slope is 0, negative 1.3, 0.13. So what do we learn from this regression? Okay. Assuming everything is all right, what does the intercept means? The intercept means that at the center of the city, the price, the log of the price is 4.84, right? So you take exponential, just cancel the log. That's what we do. EXP. Okay. And give you 126. So it's the center of city would cost you 126. Remember, it was 133 in the previous model. This model will predict the city center is cheaper. Okay. And here, if you get 30% away, so you get 1 mile away, you get 30% less expensive. It's not linear, right? You just like drop in the non-linear manner, right? Because it's a log, right? So it's constant fraction for each mile away. Okay. So how do you do it? Implement is very simple. To implement is you use the NP log function. You log the price and create a new column called log price. And you run the regression just to log price. That's it. So nothing very deep there, right? If it's same, right? You run OAS, log price over distance, the data to fit it, one line code regression. You print out the regression result. The regression result, as I said, you just care about two things, right? At least for our stage, you only care about only these two numbers, right? That's the only thing you need at the moment. We'll talk about this and this in the next class, right? But also you learn important things R square. So the R square is 21%. Okay. Let's compare this with the last one. What is the R square, if you remember? Let's see what's R square in the previous one. Why it's not moving? R square 15. Okay. If I do the log version, the R square is 20%. Okay. So I don't know what I were you, but if I were you, I don't know what you pick, but if I were you, I pick 20%. Right? This better model. Right? It means that they are not linear related, the price, the distance, right? It's more like non-linear. So that is a better fit. Okay, that's how we use it. Right? That answer the question how is R square, right? But R square also related to SST, SSR, right? The same thing, right? You can, if I have the MSC, then I can also show you that. Okay, is that clear? So once of this, of course, I probably want to draw a graph to show you what it looks like, right? I look at the X, look at the Y, and also predict the model. And remember, okay, I want to plot the price, right? So I want the Y-axis is Y, but not Y. So that's why I have to convert back by exponential. Okay. If I don't do this, I'm plotting log Y on X. Right? So let me say. Because at the end of the day, I'm not interested in, when you run the regression, you're running this line. Right? It's log Y versus X is a line. But I don't want that. I want to look at the price. So at the end, I want to look at this price. Okay. To be fair, it should be dropping, right? Okay. You turn out this something like this, right? Now we draw. So in order to convert this point to here, because log, right? You take exponential, right? Exponential is 2.713 raised to the power, right? This exponential is the Euler number. Okay. Is that okay? Okay. So let's plug it. So I prepare this and I just get the plot, right? So this is the lot price distance is what I said, right? But I don't care about this that much. No? Okay. It looks like this shape rather than what I proposed, but it looks like this shape. Okay. That means it's a non-linear one. Okay. And this fit better because it's more concentrated here, right? So it's just like it squeeze a little bit, fit better. 5% more, right? Don't overlook this 5%. The original model only have 15%. So 5% more actually is like 30% increment, right? So it's not a negligible thing, right? Before 15%, now it's 20. It's like 30% improvement on the fit. Yeah. Is that okay? So you can also do mix and match, right? Instead of looking at log of y, I can log x. Okay? I look at the price, I look at distance, right? So it's not the distance matter, but rather the percentage distance matter. Okay. And I run the regression. This number comes from the table, column. Okay. And how can you interpret this? Okay. Again, at the city center, okay, the price is 119, 116, right? And what is the slope means? Means if you are away from the city center, right? Then this gives you $128 less. Okay. If you want 1% distance away. Okay. So if you're 1 mile, you go by 1.01 mile, then you will be $28 less. Okay. So how can we run this regression? Okay. Here's some problem one in the regression that's an actual concern because when you take log and when it is close to 0, it becomes infinity. If you actually know the math, if you recall, there's some technical details here. Sorry for the technical part. If you remember something from your high school, sorry for the high school math. So this is 0 and this 1. Log 1 is 0. Let me draw it. Okay. And log 0 is infinity, negative infinity. So this look like this. So this is sorry for the high school math, but so you can see when it's close to 0, it's negative infinity. Right? So that's why we don't want this thing to happen, because when it's very small, it goes to infinity very fast. So it's not very stable. So usually what you do is you would basically cut off this thing. When it's close to 0, okay, you set to a small number. So usually in the example I give is when it is close to 0.05 or less, you set it to 0.05. It's just what we call censor it. Okay. So what I'm doing is instead of this, I look at number which is small enough is 0.05. From now on, I cut this here. So anything, I just put it up. Okay. This is my transformation. Okay. But just some technical point here. Okay. When it's very close, I just put everything from 0.05. Okay. That's what I do, right? If less than 0.05, I make it 0.05. Okay. Because log of 0 is infinity, right? So that's why that's the case. Because if the hotel actually city center, if negative infinity, so you can't really define. Okay. And the same thing goes on, take the log and then just run price over log distance. The same regression, okay? And the key is this two number, and that's it, right? At the moment, right? Later, you will use these two number to tell whether they're good or bad, but that is the idea that we have. Okay, is that a question? And again, you can draw a picture, okay? Do the prediction, okay? And this is look like this, right? This is log y and this log x. I think I copy and paste the wrong picture. I'll correct it. There's some mistake in the picture because you should only be distant, not the log distance. I check how to correct this picture. But the code is correct. Just I think I copied the wrong picture. Okay. And if you go back from a log distance to the normal one, actually it's not like linear, but you fit in this one. Okay. And you can see if you fit this model, what is R squared? It becomes 20%, right? So almost double the original one. Okay. So if you want to fit, simply change log or not log can change a lot, right? So even regression that simple, you can change. Okay. This also apply in your machine learning class, right? You need not use the original data. You can transform it. Take log, take square, can improve. Okay. So it's not just applied to our class as well, right? You can consider those transformation. Okay. And if you look at R squared, that fit much better. Okay. And you can do the same for the log case. Okay. And you have intercept and the slope. You can also define things, but the intercept means you can also say something, but I usually don't care too much about this one. And you run the same regression, and this doesn't change too much. R squared is still 20%. So when you take log on the x actually help a lot because the distance and the price is not linear. It's non-linear, right? So as long as you make the distance non-linear enough, then you fit very well. Okay. And why is non-linear in this way? Because the distance away from the city center at the beginning is very important, right? Within 1 mile, say, for example, the idea is like this, right? We have to, beside the math, probably want to know some economics or some reasoning. Why this fit better than a line? Why you take the log of x will improve? The reason is, look at this, is when you close to the city center, right? You walk away one street or two street, okay? The price would drop a lot, right? Because you no longer can walk to the city, right? And then what's different between 2 or 3 or 4 miles? You drive already or take a car or public transport already. So the first few miles is very expensive, right? Look at all the houses, right? If you are close to this subway station on the top, then charge a lot of price, right? And 1 or 2 miles, then it's a lot of drop, right? But if you further, then it doesn't really matter anyway, right? So that explains why this model, right? You don't just blindly think about running regression, right? You should use the domain knowledge to see which model will fit better. This is something you should be able to do, not me, because you know what you're running regression, right? If you just blindly run regression, why you need to learn, right? You just fit in the machine learning model or ask undergrad to run it, right? Undergrad can do it, right? Why you have to teach this to you, right? Because you have to know, right? Your staff, right? Your junior run the regression, right? You tell him which regression to run, right? Then you have to know which one is better, right? Of course, he or she may not know R square, right? You can tell him, give me R square, you can pick, right? At least, right? But the better thing is you have to tell him, okay, this is the thing. Okay. So this is all plotting the graph. I'm not going to go into detail. Okay. So I want to show you one very powerful package, okay, which usually is very useful to combine different regression into one table, which is called the star glazer. Okay. And you have to install it. If you want to install it in the code lab, you have to use exclamation mark PIP install star glazer. Okay. The code is like this. If you look at my code, you'll be here. So you install it. Okay. Once you install, you can combine the regression yourself. Okay. How to do that? The code is very funny. From star glazer, dot star glazer, import star glazer. Okay. Don't ask me why. This is the code because it's so important. You want you to repeat 3 times. I don't know. Don't ask me. This is the code. Okay. Every code is like the menu is right there. Star glazer, dot star glazer, import star glazer. Okay. So the star glazer is you combine different regression. Okay. And these are just give the name. You order them distance, log distance, intercept. And you call the column is price, log price. These are all cosmetic. So these 2 are cosmetics. So you can basically skip. They can basically skip everything here. Okay. It just improves the cosmetic. Okay. And why it's good? Because once you run it, it gives you this professional looking table. Okay. And this actually even is good for academic publication. It's good enough for all professional purpose. So you will see from this one, okay, you will see the R square, how it changed from model 1, 2, 3, 4. Okay. Model 4 actually very good. It's 33%. It's like 2 times than the original model. Okay. And you can also look at the residual center error is the RMSE, right? So it's also changing a lot, right? It's and dropping, but it's not easy to compare because they're in different dimension. So that's why they drop because of the law. So if you want to compare, you take the exponential, have to. Otherwise, it's not fair comparison. But anyway, that's why you would focus on R square. Okay. And the package is called star glazer, which means that, okay, stars. Okay. We'll talk about it in next class. But what you want is you want 3 stars. Okay. If 3 star, that means that your regression is good. If no star, your regression is garbage. Okay. And we'll talk about star later. Star means that the p-value is less than 1%, or less than 5%, or less than 1%. Why? What this is, you compare this to 0. You test the hypothesis whether the coefficient you guess is different from 0. If different from 0, your model is valid. If not different from 0, the model is garbage. Okay. So that's why this we will do in the next class. Okay. We'll do this. Okay. There will be something left for the case study, but we cover almost the main thing there. Okay. So 1 minute, you can leave early. It's before 9:30. I see you next week.